Scientists get into a lot of stuff that can easily get out of hand and put us in trouble. While many movies exploit the scientific experiment gone wrong, create a monster or hero trope, our magnetic field has actually come under pressure by an experiment conducted by CERN scientists. The Earth's magnetic field was cracked open days after the Large Hadron Collider was turned on, leading to a totally unexpected outcome. Magnetic monopoles may not mean much to the average person, but scientists are deeply interested in them because of the effect they could have on the universe. This is why scientists spend a lot of time looking for these weird objects. But where did the idea of monopole come from, and what could be the effect of monopoles on the universe? To understand and appreciate why scientists devote much of their time to it, let's start at the beginning. We go back to the turn of the 19th century when little was known about electricity and magnetism. It was widely accepted that there was such a thing as an electric charge that came in two types, where like charges repelled and opposite charges attracted, and that electric charges in motion created currents, what we call electricity today. We also knew about permanent magnets, which had one side that acted as a north pole and the other as a south pole. However, no matter how small you chopped up a permanent magnet, you'd never end up with a north pole or a south pole by themselves. In other words, magnetic charges only came paired up in a dipole configuration. Several discoveries made during the 1800s helped us make sense of the electromagnetic universe. We learned about induction, which is the process by which moving electric charges generate magnetic fields, and how changing magnetic fields in turn induce electric currents. We also discovered electromagnetic radiation and how accelerating electric charges can emit light of varying wavelengths. And when we combined all of our knowledge, we discovered that the universe was not symmetric in terms of electric and magnetic fields and charges. Maxwell's equations only have electric charges and currents. There are no fundamental magnetic charges or currents, and all magnetic properties that we observe are actually caused by electric charges and currents. Mathematically, or from a theoretical physics standpoint, it's very simple to modify Maxwell's equations to include magnetic charges and currents. Simply add in the ability for objects to also possess a fundamental magnetic charge, an individual north or south pole inherent in the object itself. When you add those extra terms, Maxwell's equations change and become completely symmetric. Induction now works the other way around. Moving magnetic charges generate electric fields, and a changing electric field can induce a magnetic current, causing magnetic charges to move and accelerate within a magnetic current-carrying material. But for a long time, all of this was merely speculative thought until we began to recognize the roles that symmetries play in physics and the quantum nature of the universe. It's possible that electromagnetism is symmetric between electric and magnetic components at some higher energy level, and that we live in a low-energy, broken symmetry version of that world. Although Pierre Curie was among the first to recognize the existence of magnetic charges in 1984, it was Paul Dirac in 1931 who demonstrated something remarkable: that if there was even one magnetic charge anywhere in the universe, it quantum mechanically implied that electric charges should be quantized everywhere. This is fascinating because when it comes to quarks, not only are electric charges quantized, but they are quantized in fractional amounts. One of the most powerful hints we have in physics that new discoveries are on the way is the discovery of a mechanism that could explain why the universe has the properties we observe it to have. However, none of this proves that magnetic monopoles exist. Rather, it merely suggests that they might. But scientists have not given up on looking for monopoles, and it's important they don't. Why? Whenever scientists consider a theoretical idea, one of the things they look for are pathologies. That is, reasons that whatever scenario they're investigating would break the universe in some way or another. When 't-Hooft-Polyakov monopoles were first proposed, one such pathology was discovered. Magnetic monopoles would do something known as overclose the universe. In the early universe, things are hot and energetic enough that any particle-antiparticle pair you can create with enough energy will get created. When symmetry is broken, you can either give a previously massless particle a non-zero rest mass, or spontaneously rip a large number of particles or particle-antiparticle pairs out of the vacuum. The first case is what happens when the Higgs symmetry breaks. The second case is when the Pache-Quinn symmetry breaks, allowing axions to escape the quantum vacuum. In either case, this could have disastrous consequences. The universe normally expands and cools, with the overall energy density closely related to the rate of expansion at any given point in time. If you either give a large number of previously massless particles a non-zero mass, or add a large number of massive particles to the universe suddenly and spontaneously, the energy density increases rapidly. With more energy present, the expansion rate and energy density are suddenly out of balance. There is simply too much stuff in the universe. This causes the expansion rate to not only fall, but in the case of monopoly production, to fall all the way to zero before contracting. In short order, the universe collapses, resulting in the Big Crunch. This is known as overclosing the universe, and it can't accurately describe our reality. We are still here and nothing has recollapsed. This conundrum is also known as the monopole problem, and it is one of the three primary drivers of cosmic inflation. In the same way that inflation stretches the universe from whatever its geometry was previously to a state indistinguishable from flat, solving the flatness problem and imparting the same properties everywhere to all locations within our observable universe, solving the horizon problem, it can solve the monopole problem as well, as long as the universe never heats back up to above the grand unification scale after inflation ends. How have scientists been looking for magnetic monopoles? In 1981, experimental physicist Blas Cabrera built a cryogenic experiment involving a coil of wire explicitly designed to search for magnetic monopoles. He reasoned that by constructing a coil with 8 loops, if a magnetic monopole ever passed through the coil, he would see a specific signal due to the electric induction that would occur. Passing one end of a permanent magnet into or out of a coil of wire induces a current, but passing a magnetic monopole through that coil of wire should induce an electric current that corresponds to exactly 8 times the theoretical value of the magnetic monopole's charge, due to the 8 loops in his experimental setup. However, if a dipole passed through, there would be a signal of +8 followed by a signal of -8, allowing the two scenarios to be distinguished. Now, on February 14, 1982, no one was in the office monitoring the experiment. Cabrera returned the next day and was astounded by what he saw. The experiment produced a single signal that was nearly identical to what a magnetic monopole should produce. This sparked a lot of interest in the project. Did this imply that inflation was incorrect and that we actually lived in a universe with magnetic monopoles? Did this imply that inflation was correct and that the one monopole that should have persisted in our universe happened to pass through Cabrera's detector? Or did it imply that this was the pinnacle of experimental blunders, a glitch, a prank, or something else that we couldn't explain but was clearly erroneous? A slew of copycat experiments followed, many of which were larger, ran for longer periods of time, and had more loops in their coils, but no one else ever saw anything resembling a magnetic monopole. But the search for monopoles has been heartily taken up by CERN and its scientists. The Large Hadron Collider, or LHC, is the world's largest and most powerful particle accelerator located at CERN. The LHC is comprised of a 17-mile or 27-kilometer ring of superconducting magnets and a series of accelerators that fire high-energy particles through the apparatus like a bullet through a gun. The collider, which is located 328 feet or 100 meters below ground, blasts a beam of protons in one direction while another beam travels in the opposite direction. At maximum speed, the particles collide at 99.9999991% the speed of light. Every time protons collide, a complex spray of other particles is produced. Many of these particles have a lifetime of less than a second, but they leave a trail of subatomic breadcrumbs that scientists can follow. Scientists rely on two highly complex detectors to follow that trail, which allows them to see the fundamental building blocks of our universe. Atlas is one of these detectors, the machine, which is about 148 feet or 45 meters long and 82 feet 25 meters tall, assisted in the discovery of the Higgs boson. Atlas is half the size of Notre Dame, the cathedral, not the university, and twice the weight of the Eiffel Tower, the one in Paris, not Las Vegas. CERN scientists use Atlas and other detectors, ALICE, CMS, LHCb, LHCf, to investigate topics that are only discussed in science fiction, such as whether other dimensions exist, what type of unifying force exists in the universe, and whether there is evidence of dark matter. Atlas and CMS were the only detectors dedicated to solving the Higgs boson mystery. All experiments at the LHC are unique and are run by a global collaborative team of scientists. It's one thing to smash particles together at nearly the speed of light. It's quite another to interpret the data generated by those collisions. Particles collide nearly 600 million times per second in the LHC. The information emitted by those crashes can tell us a lot about the inner workings of the atom and the forces that hold it together, but we can't record everything from the detectors. Atlas, for example, could fill 100,000 CDs with data every second if CERN did. Instead, Atlas, like the other detectors, can only record a smidgen of data, equivalent to about 27 CDs per minute. During reconstruction, scientists tested their theories about how particles behave. They contrast computer-simulated collisions with real-world collisions. A difference between the two could indicate new science, something previously unknown. Every day, the data center processes 1 petabyte of data. To hold all of the information in a petabyte, 223,000 DVDs would be required. To make matters worse, scientists sift through 30 petabytes of data each year, making new science extremely difficult to find. And now, a new class of experiments at the Large Hadron Collider at CERN, first envisaged by imperial physicists, have created conditions more likely to produce monopoles. Despite the fact that no monopoles have yet been discovered, the new experiments have allowed researchers to fine-tune the likely properties of monopoles, directing the course of future experiments. While physicists' ability to draw conclusions from previous experiments at the LHC and elsewhere has been limited, these new experiments, which use a different production mechanism, allow us to definitively rule out the existence of certain types of monopoles and have given us a much better idea of where the search for monopoles can go next. In 2018, the LHC smashed together a different kind of particle, heavy ions in the form of lead nuclei. Because these particles contain hundreds of protons and neutrons, they can only collide at lower energies than single proton collisions. However, if these lead nuclei clip or pass very close to each other, the interaction can produce something spectacular. The universe's strongest magnetic fields are 1,000,000 times stronger than those found in neutron stars. These exist for a very short time, but they provide a different mechanism for producing magnetic monopoles. The theory is based on a mechanism for producing electrons and their antimatter equivalent, positrons, the electrical equivalent of monopoles. According to the Schwinger mechanism, which was proposed in the 1930s, a strong electrical field will interact with quantum fluctuations in a vacuum, producing electrons and positrons. A strong magnetic field should also produce north and south monopoles. While no evidence of monopoles was detected, the organization made a very strange announcement. A crack in the Earth's magnetic field appeared and remained open for nearly 14 hours. A rare phenomenon known as a co-rotating interaction region (CIR) from the Sun caused the crack in the magnetic field. CIRs are large-scale plasma structures formed when fast and slow-moving streams of solar wind interact in the heliosphere's low and mid-latitude regions, which include the solar magnetic field and the solar winds. CIRs, like coronal mass ejections, CMEs, are flung out from the Sun towards Earth and can contain shock waves and compressed magnetic fields, resulting in stormy space weather, which usually manifests as beautiful aurorae. Coronal mass ejections, like solar flares, are caused by the twisting and realignment of the sun's magnetic field, a process known as magnetic reconnection. When magnetic field lines tangle, they produce strong localized magnetic fields that can break through the sun's surface at active regions, resulting in CMEs. CMEs typically occur near sunspot groups and are frequently accompanied by a solar flare, though the two do not always occur simultaneously. CMEs, like solar flares, are most common during solar maximum, a period in the sun's 11-year cycle of activity when the star is at its most active. CMEs swell in size as they travel away from the sun after they're released. Larger CMEs can fill nearly a quarter of space between Earth and the sun by the time they reach our planet. If a CME is large enough and travels faster than the solar wind, it generates a shock wave in which accelerated charged particles travel ahead of the CME, disrupting space weather conditions and intensifying geomagnetic storms. And while CMEs produce beautiful auroras, they can be destructive. Large CMEs can cause technological malfunctions, which are especially troublesome in today's world. For example, the Carrington event in 1859 disrupted the global telegraph system. There were even reports of operators getting electric shocks and sparks from telegraph machines igniting papers. And according to NASA, a CME accompanied a solar flare that hit Earth in 1989, causing an electrical blackout that lasted 12 hours in the entire province of Quebec, Canada. The event caused at least $10 million in damage to Quebec's utility company, Hydro-Quebec. But how exactly do CMEs cause all of this havoc? CMEs can cause electrical current surges that overload power grids, resulting in widespread blackouts. And that is in addition to jostling the Earth's magnetic field, impairing radio transmissions and increasing radio static in the ionosphere. GPS systems are especially vulnerable to ionosphere disturbances, and GPS coordinates have been known to stray by tens of feet during a CME event. GPS uses radio signals to relay information between a satellite and a ground receiver, which causes the disruption. The radio signal passes through the ionosphere layer, which contains charged plasma that bends the path of the GPS signal in the same way that lenses bend light. Normally, GPS systems can compensate for this bending of the radio signal, preserving GPS accuracy. During a CME event, however, the ionosphere can be so severely disrupted that GPS models are unable to keep track of such changes, and receivers are unable to calculate an accurate position. Also, Earth-orbiting satellites are vulnerable to CMEs, particularly those in high geosynchronous orbits, which is where the majority of communication satellites are located. Satellites can be struck by a high current discharged into the satellite or damaged when high-energy particles penetrate the satellite when a CME causes a geomagnetic storm. As a result, vulnerable satellites can be put into safe mode to prevent electronic damage. SpaceX saw firsthand the devastation that space weather can cause last year when a geomagnetic storm destroyed up to 40 Starlink satellites, worth more than $50 million in February. The magnetic field protects us against solar storms caused by the sun. It was previously thought that they opened and closed quickly, but we now know that they stay open for hours. Scientists discovered that our magnetic shield is drafty, like a house with a window left open during a storm. The house deflects the majority of the storm, but the couch inside the house gets destroyed. Similarly, our magnetic shield absorbs the brunt of space storms, but some energy escapes, causing problems with satellites, radio communication, and power systems. And the sun is nearing its most active period in the solar cycle around July 2025 and is already unusually active for this early in the cycle. What this means is that your chances of seeing the aurora are now excellent, and they will continue to improve over the next 3 years. Now, there are valid reasons to be concerned about the effect of something happening to the Earth's magnetic field. Perhaps the most terrifying effect of losing the Earth's magnetic field might be losing the air we breathe, and the culprit would be the solar wind once again. The sun's natural wind is so powerful that it can easily rip gases from a planet's atmosphere until there is no gas left. In fact, that is most likely what happened to Mars. Mars was most likely once similar to Earth, with oceans of water and a dense atmosphere. But unlike our planet, its magnetic field vanished billions of years ago. Its atmosphere was completely unprotected and it was ripped away into space. When its atmospheric pressure fell low enough, its water began to evaporate and was carried away by the solar wind too. It's entirely possible that without our geomagnetic field, our atmosphere, oceans, and life on Earth would perish in the same way. But before the atmosphere is stripped away, animal life would be affected on our planet. Humans aren't the only animals that use the Earth's magnetic field to guide them. Many birds, sea turtles, lobsters, honeybees, salmon, and even fruit flies have biological compasses known as magnetoreceptors built into their bodies. During the winter, birds use this ability to migrate to warmer climates, while sea turtles use it to navigate the open ocean and find beaches to lay their eggs. Scientists believe that most female sea turtles return to the same beaches year after year, thanks in part to their natural compasses. Many animals that rely on compass navigation could be in serious danger if the Earth's magnetic field vanishes. Sea turtles can become disoriented at sea. Migratory birds may fly in the wrong direction, endangering their lives. Honeybees may become disoriented while searching for their hives, affecting flower and plant pollination. These and many other organisms may face extinction as their navigational abilities deteriorate. Let's hear what you think of the Earth's magnetic field in the comments section below.